direct products of, well, the title is Games and Graphs. Two things that I really talked about were this notion of a lifting theorem, which I'll now return to, and also kind of direct products of games. Functions or strings is what I'm going to talk about today. And then I also talked about in my previous lecture, which was more of a survey about direct products of games, which are also known as parallel repetition, and this is what I'm going to talk about on Tuesday in my last lecture. And in between, there's also this direct product of graphs, which I'll mention in both talks. And also, if you noticed, Ehud Friedgut was talking about it. So he was talking about a particular question, which is studying the maximal independence set in a direct product of graphs, in a graph power. And I'll try to connect these things. So today, I'll focus on this direct product of functions. And I'll remind you of this picture that we had. So actually, maybe I will draw it here. So we had some universe with n elements. And then we were considering the situation where we have local views of this universe, some subsets S. That's prime. And we're considering this situation where we have an alleged restriction of there is some global function telling us the state of the world. And then we have local views of this. So in each local view, we get some restriction of this function to a specific subset of bits. So the ideal situation is that there is some function, some n-bit string or some function like this. And then for every s, we have access to this restriction of the function to some subset s for every s in n. And I'm focusing on subsets of some specific size k. And let's think of n as being very large. So it goes to infinity. And k is maybe a constant, or maybe it's slightly growing with n, but like log n. Okay, this is the kind of regime that k I'm thinking about. Large constant, or maybe log n. But n is much bigger. Okay, so the ideal situation is that I have some function, capital F, which gives me local views. So capital F maps all the is defined on all subsets n choose k. And for each subset, it gives me a string of k bits such that f of s is equal to f restricted to s. So this is the ideal situation. F, for every local view, the value of f on this local view is consistent with some global function f. Now the kind of question that I want to study is the local to global question. What if I know I'm given some capital F, and I don't know that it's an ideal capital F, that it really comes from one global function? What I do know is that capital F obeys some kind of local consistency condition. So for example, pairs of S's that have some intersection usually agree. And from this, I want to deduce the existence of a local F. The existence of a global F. Right, so it's a local to global phenomenon. we have it in various contexts, so this is the context I'm interested in. So, so this, let me write local to global lifting. Lifting. Okay. So it's you want to deduce from a local consistency. It should imply some kind of correlation with the global function. Okay. All right, so let's see several contexts in which we have this kind of situation. Okay, so in fact, let me first formally define what a lifting theorem is. Okay, so a lifting theorem. Okay, so I want to formally define what this is. So I have some collection of subsets. So A is a subset of n choose k. Right, so this notation means n is the set of all elements from 1 to n. N choose k is all k element subsets of the elements from 1 to n. Okay, so now I have some collection of subsets A. It might not be all k element subsets, might be some family. But to begin with, let's even think of A being equal to this. Okay? And then what I have is some kind of consistency graph. So for each element in A, so here are the elements of A. Okay? I'm drawing now a graph. And so this is S prime. All of these are different k element subsets. Okay? So this picture is different from that picture. Here the points were just elements of N. And now the points are subsets, are elements of A. Okay? And now I'm going to put an edge between two subsets if their intersection has cardinality exactly t. Okay, so Et is the collection of all SS prime in A squared, I guess, such that S intersect S prime has size exactly t. Okay, so now I defined a graph on vertices A, and these are the edges, Et. Okay, and this is what I will refer to as the consistency graph. Okay, so G, which is A and Et, is okay. I guess my picture is taking too much space. Is the consistency graph. Right. And now, what am I interested in? I'm interested in the situation where I'm given a labeling of the graph. So given f from the vertices to a set of labels, which in my case will be 0, 1 to the k. So remember, it's exactly like the intuition we said. For every subset that we are considering, every element in A, we have some string which supposedly is the local view. Supposedly it's like what this subset thinks that the value of these elements are. Okay, so we're given this labeling, and we know that it's pairwise consistent to some degree. So what does that mean? It means if we have this graph that I drew and then erased, this is the graph whose vertices are A, and I connect S and S prime if their intersection is exactly of cardinality t. So, of course, this is some specific graph on the vertices A. You can think of other graphs, maybe connect to if the cardinality is at least t or whatever. Or maybe some weighted graph. Okay, this is the graph for now. And what I'm given is some kind of knowledge about pairwise consistency. So I know that the probability when I choose, sorry, S and S prime. So this notation just means that I choose a random edge in the graph. Okay. So it means SS prime in ET. So it's the same thing. probability of choosing S and S prime, and then I look at f of S, and I look at f of S prime, and I want to say that they are consistent. So what does it mean? So these are two subsets. They have some common intersection. So the picture I have in mind is this, and these are some T elements. So consistency would mean that the restriction of the, so S prime gives some value to 0, 1 value to each of the elements here, and I just want that the value on the intersection is the same. So my notation will be that f of S restricted to the intersection S intersect S prime equals okay, so this just exactly checks what we intuitively think, that S and S prime have some common elements, and they need to have the same opinion about these common elements. Okay, and then I know that this probability is at least some alpha. Okay, and for now, let's think of alpha being, I don't know, close to 1, like 1 minus epsilon. Okay. So, so what do I have so far? I have a graph, and I have some f, which is a labeling of this graph with these local views. And I know that they're alpha consistent, so like with probability alpha on a random edge, they agree. And now I want to deduce a lifting. So then there exists some function f, 0, 1, such that, okay, so what can I conclude? That the probability, when I choose a random s in A, that f of S equals f restricted to S. This probability should be, I don't know, bigger than some beta. Okay, so this is a lifting theorem. It says if the pairwise consistency is something, then there is some global function such that f of S is consistent with this something. Okay, and for example, one parameter setting is when alpha is 1 minus epsilon. I guess this looks white, but it's supposed to be blue. And then this is also 1 minus O of epsilon. Okay, and then we have a couple of parameters that we have here. We have T, which is the intersection size. So of course we have N and K. And you can even say that I didn't specify what capital A is, or calligraphic A. Let's for now think of A as being equal to just K. So I have this parameter T, and then I have these parameters alpha and beta. And I can also have some parameter here, like some delta here that says, I will deduce that f agrees with some global function approximately, in the sense that for random S, if this is a k-bit string, and this is a k-bit string, if they agree on 99% of their coordinates, that's also good. So there can be this delta parameter. All right, so this is if I have a lifting theorem with these parameters, it means that for every labeling for which the pairwise consistency is at least alpha, there's some global reason, that agrees with this f on at least beta. Okay, so that's what I would mean by a lifting theorem. And now, today I want to talk about various lifting theorems that I have. Okay, so so I will have several cases here as we go along. So the first one will be where A equals n choose k. Okay. And then also alpha is close to 1. So we write like this, alpha is 1 minus epsilon. All right, so this is the first case I want to discuss. Yeah. Right, so, so this kind of questions came up in the construction of probabilistically checkable proofs. And actually, the first to consider this that I know are Goldberg and Safra. And they proved a lifting theorem of this form with this set A and when alpha is close to 1. But they didn't consider this consistency graph that I drew, but rather a consistency hypergraph. So really, there's no reason when you're given this labeling and you want to know if it's globally consistent, there's no reason to just check a pairwise consistency between two sets. You can look at three sets and say, I look at the first set, and then I have some set that intersects it, and maybe I have some other set that intersects that, and I want to see that if everything is consistent, and this happens with probability 1 minus epsilon, then I want to deduce something. So kind of a more general framework than what I just said is to talk about a consistency hypergraph. But I really am interested in a hypergraph that only, makes a few queries to this labeling function. So we think of this labeling function as some long proof oracle, and then you query it. So here you're querying it at 2 points. If it's a hypergraph, you're querying it if it's R uniform, you're querying it in R points. So I want the R to be constant, like 3 or 4. So R uniform hypergraph, but with very small size of the hyperedges. Okay, but in general, you understand this, right? So I have the same. The vertices are just a bunch of subsets, and then I might have some hyperedges. The way to define them I haven't said yet. Anyway, so they proved some kind of lifting based on 4 uniform hypergraphs. Oh, okay. I started getting smaller. Yeah, okay. So for query lifting, I think it's 4 actually. I'm almost sure. Okay, so for query corresponds to this picture with 4 uniform hypergraphs. And then with Omer Reingold, this was like in maybe a few years ago, like in 2003 maybe, we tried to construct some. So Goldberg and Safra also, the reason they were doing this was to construct some combinatorial PCPs. And with Omer, we were trying to do a similar kind of agenda. And we proved the lifting theorem of this form. So we proved the following thing. If t equals k to the 2/3, so here, this is my situation. My set of elements is all k tuples. And I put an edge between two subsets if they intersect on some square root of k elements. Well, not square root of k, k to the 2/3 elements. Okay. And alpha is 1 minus epsilon. Then can lift with beta 1 minus O of epsilon. So I don't know if this is the best way to write it. The point is that what we proved is that for any labeling you have here, such that the graph is defined with intersection size k to the 2/3, if the probability of having local consistency is at least 99%, then there is some function, some global function f, such that your labeling must be consistent with probability 98%. Okay, so 1 minus O of epsilon. What about delta? So delta, if we think about it, you'll see that delta must be non-trivial. So it can't be that delta here is 0 in this theorem. Okay, why? So delta, the correct value for delta is t over k, which in this case is sorry, t over k. Okay, so Yeah, so it's k to the minus 1/3. So what does this value mean? What did I mean by delta? I mean that they agree up to, at most, this fraction of errors. Okay, so if I count it as a number and not as a fraction, okay, fine, so times k. Actually, I'm not sure if this is the right thing, or it's or it should be k to the 1/3. Okay, so something is confusing me, but let's kind of gloss it over. I'll show a proof, and then we will find out. So the point is this: if you have so this is what we proved, and kind of a weird thing about this is, why does t have to be exactly k to the 2/3? Everything else seems fine. I mean, there is some natural way to relate t and delta. So actually, let's see that. That will help me. So the constant in the
beta equal to say 1 minus c epsilon.
Right.
C is independent of t and k.
Right. Yeah. So we think of t, k, and n as not constants. Or every time we write a constant, it's illegal to hide t and k and n inside of these. So it's just a constant, independent of these other things. What is the relation between delta and t? Okay, so let's find it out, right? So suppose I have some function f, arbitrary. Okay, and then I define f by a two-step thing. First of all, set f of s to be f restricted to s, and then randomly, and then for each s, first you set it to be f restricted to s, and then you randomly flip some r coordinates. Okay. So now, how many coordinates can I flip and still have this capital F pass with probability close to 1? So suppose I only flip one coordinate. Okay. So now, if t is like k to the 2/3, and I look at two subsets that intersect on k to the 2/3 element, both of them mostly agree with the same global function, except that there was this one random perturbation. Now, since the size of the intersection is little o of 1 of the entire set, the probability that this perturbation occurred in the intersection is o of 1, little o of 1. And so this function will pass the test with the probability very, very close to 1. Okay, so for example, if I flip only one coordinate and t is some little o of k, then this function will pass with very high probability. So this kind of shows that I must allow some delta in my conclusion. Okay, so really the relationship is that I guess there is something like r times t, r over k times t. Okay, maybe someone can help me here. So with probability t over k, I catch one of these things. So this, as long as this should be some constant, right? So for this theorem to hold. Okay, so I guess here t was 2/3. So the number of guys is k to the minus 1/3. So this should be actually k to the minus 2/3 maybe. Sorry?
So delta is not t over k, it's just k to the minus 2/3.
K is not t, or delta is not t over k, but rather it is, it's 1 over t. Okay, sorry about that. I should have prepared this. Okay. So that's the correct thing. It's just 1 over t. So that you expect to have at least some constant probability of catching even these random perturbations. Okay. So then
In the last
considered like k tuples, like the graph was over 10 raised to k.
Oh, thank you. Yeah, okay. So Girish is saying that now I'm considering this situation where it's k subsets and not ordered k tuples. So right, this is kind of something I usually like to ignore. So when k is very small, like log n and n is n, then these two things are proving one kind of theorem implies the other and vice versa. So somehow for today this is more convenient for me. But it's true that when k becomes large, so when k is small with respect to n, then a random k subset will not have repetitions, and so it's the same. When k is larger than square root n, or I don't know, then you will have repetitions, and then these things start to diverge. I mean, the other situation is also interesting, but okay, not today. Okay, so kind of then there was a lot of, or there was some work on alpha being close to 0. But before I move to that, I want to say that this work with David Steurer from last year, we proved kind of this theorem, but for all values of t. So we proved lifting for all t. Well, maybe more correctly, t is 1 minus some, not delta, I don't know, eta times k for all t. And alpha in this regime of being close to 1. Okay, so the same kind of regime, but now it's for all t and with the correct delta. So delta is 1 over t. Okay, so all right, I'm going to kind of quote more results, but I want us to get some feeling of what is going on and what is the kind of thing you argue when you prove such a theorem. So I want to show you a proof of this kind of result, these two results. Okay, so I won't give a full proof. I just want to give the intuition and kind of show you where I run into problems. Hopefully this will be good enough. Okay, so let's
So just a general question. So is this really telling us what the theorem should look like? So are these in effect the hardest cases?
yes, yes. So up to the constant. So if you don't care about the constants exactly, then we essentially prove that when you have this relationship, so delta is 1 over t, and your success is still 1 minus epsilon, it's because of this structure. Okay, so this is the general thing. You want to show that something happens. The only reason for it is the specific structure that you have your hands on. Okay, so how do you prove this? So how to prove lifting? Okay, so we are given. So what are we proving? Given some f. So here, from n choose k to 0, 1 choose k, and is fix some t, and fix, I don't know, some t. And we consider this this graph. Do I have it here somewhere? Okay, I have here this graph. And I already know, I'm given, that the probability of choosing a random pair of subsets that intersect on t elements this is bigger than 1 minus epsilon. Okay. And now I want to prove find some function f such that it agrees with this capital F most of the time. So I'm given this labeling this collection of local views. It has some pairwise consistency with probability 1 minus epsilon. I want to find a global reason such that the probability that f of s equals f restricted to s, well, up to this delta, I guess let me write 1 over t. This is also bigger, it's also big, like this. Okay, so this is my goal. Now how will I do it? So actually, the first steps are rather easy. I mean, what are you going to do? Your first step is you want to find f. What are you going to do? You have a bunch of local views. They're usually consistent. What will f be? I want to say what is f of 1, what is f of 2, f of 3. Okay, so what will be f of 1? You look at all the local views that have some opinion about 1, and you take the majority value. Right, so define f by majority. This is obvious. And now, what you have left to do is to prove that this f that you've defined is good. It's consistent with f of s. Now, why is this okay, so is it a two-line proof? It's not. And the reason is that now, kind of, if you do some kind of averaging, you will see that if you look at some random f of s, and you look at f restricted to s, okay? Then just because of the probability of two random elements to agree is 1 minus epsilon, maybe you think that on 1 minus epsilon of the coordinates you agree with the majority function, but this is not exactly what you want. I mean, you want to agree with the majority function you want a better agreement. I mean, epsilon is some constant, and so you kind of need to work a bit harder, right? So, step 2 in this proof will be okay. So let's look at all the. Let's consider all the subsets S. That are not in this agreement with little f. Okay, so now I've already defined my little f, and all I have left is to prove this thing. Here? Ah, sorry. It's agreement, but then there is this parameter delta. Okay, and here delta is 1 over t. So what is meant here is that these are two k-bit strings.
No, that's fine.
That's fine. Okay. And they agree on all but delta, a fraction of their coordinates. Okay, so now I defined already little f, and my remaining goal is to prove that now capital F agrees with little f almost always. Okay, so let's look at all the sets S for which this fails. Okay, so all subsets S such that the number of indices such fs I is not equal to fi is bigger than delta times k times some constant. Okay, so I'm now considering all subsets for which the fraction of coordinates on which they disagree with f is big. It's too big. Okay, these are the ones that prevent me from proving my theorem. If there were not any such subsets, then this probability would be equal to 1. Okay, so these are the bad guys, and I need to show that there are few. So we'll call them bad. Oh, okay. Now, and also for each subset S, it's useful to look at these coordinates, all the i's for which there is inconsistency with the f, and call these coordinates the wrong coordinates. Okay, so in every subset S, there is some set of coordinates that are wrong, and the bad is all subsets S such that wrong of S is bigger than a delta k times a constant delta k. Okay. Okay. And now what I want to show is that if I have some set in bad, then whenever I look at a random edge in my consistency graph, S and S prime, with some constant probability, this edge will detect an inconsistency. So I have a picture of this graph. Right, so this is my graph. What I know is that when I select a random edge in this graph, and I check f of s and f of s prime, then they agree with probability 1 minus epsilon. So if I show, suppose these are the bad s's. If I show that, on a bad vertex, a lot of the edges are rejecting edges, even if it's inside. If I show that on a bad vertex, many of the edges are edges that reject, then it will show that the size of this set must be small. Okay, so S is bad. So, probability of choosing S prime neighboring to S such that f of S on the intersection is agrees with f of S prime, or conditioned on S. This should be some constant. Sorry. Okay, so this is what I want to show, that if I have a bad S, then no matter if I choose a random S prime according to this graph, then they will disagree with some constant probability. Okay. However, this is wrong. This fails. Why does it fail? It's because this graph, S and S prime are not independent. So, think of S. It's some subset. This is S, and there is some set of wrong indices. So on these indices, the local view of S is not in agreement with the majority opinion. Okay? So now, how do I choose S prime? First, I choose some random subset of T elements, and then I add some more. So S prime is this and this. So it's some set of elements that also is in S, and some extra collection of K minus T elements. This is S prime. Okay? So now, if in this intersection there's exactly one wrong element, and if S prime were a random subset that contains this wrong element, then, it has constant probability of agreeing with the majority function. And then, okay, so I'm now trying to explain why we thought that this should work. Why did we think that this should work? So we started with S. Then we look at the S prime that intersects it randomly. And pretend that the following thing happened. In the intersection, there was one wrong element. And, S prime was some typical S prime that contains this element. So if it was a typical subset that contains this element, then just by the way we define the majority, on at least half of these elements, on at least half of these S primes, the value agrees with the majority. Whereas on S, you agree with the minority. And then they would reject. So this would explain how S and S prime should usually reject, or with some constant probability. However, S prime is not a typical subset that contains this element because it's much more correlated to S. It agrees with S on all these other coordinates. Okay, so it's not a typical subset, and that's why this argument is wrong. However, this is not so bad because if you look at the graph of all subsets that contain this element, then this graph has the same structure as almost the same structure as this graph. It's just like you're looking at n-1 as the universe of size n-1 and choosing k-1 subsets. You fix this element to be in all of these sets. And this graph is a good expander. So, I mean, you can either, I guess you can trust me on this, but this is true as long as T is some constant fraction of K, not too close to K. Okay, remember we talked about this last lecture that if T equals K, you're really stepping in place. You're choosing S, some k element subset, and then S prime is going to be the same k element subset. So it's nothing. But once you let t to be smaller, you start like moving around. And even if t is, I don't know, 0.9 times k, the graph is already an expander. And then this kind of argument can show that, okay, maybe not every edge goes out many times, but the fraction of edges that they reject is proportional to the number of vertices. This is what happens in an expander. And then the proof is done. But actually, this is not even the most difficult part. The most difficult part is due to the fact that inside this intersection, there could be more than one wrong element. The number can range. And somehow, you would feel that if there's more, it's even in your favor, but that's not true. There is some non-monotone behavior that makes it difficult to kind of control the double counting. And so, like in this work with Omer, we could only do it for small t's, for this, k to the 2/3. In the work with David, we do it for all t's, but kind of the proof doesn't look like this at all. So I feel like I still don't know the correct proof, but at least we know the correct theorem. So this is the situation. All right, so, I mean...
But can't you just argue that if you know that S and S prime has intersection of t, then you know the expected number of how many of the bad elements they have in common?
Yeah, so if I knew that... so there's this set of bad S's. These are S's that have this many wrong elements. If I knew that all the S's have this many wrong elements, then I can do what you said. But my problem is that many of the S's can have like k wrong elements. And because I can't control this, then somehow I don't know what to do. And I don't have any tool to, or at least I don't know of a good way to do it. And like I feel there should be, but I don't know. All right, so this...
phenomenon, by the way, in property testing, right? That if you lie a little, then it's very easy to catch you. But if you really lie boldly,
There are various professions where
Right, that's very good, actually. Yeah, thanks. Right, so that's true. Somehow, this is this non-monotonicity that's maybe not intuitive. If you lie more, you actually are in better. The adversary is somehow in better shape. Yeah. Yeah. Okay. All right. So, kind of my goal in this is not a proof, but I don't want to give a real proof because it will take all of my time, and I don't know what value it will have. So let's just see what we did. We wanted to prove a local to global thing. The first thing we did is define the global object. So here it was very easy. It's just by majority. And then you want to prove that the global object works. And so it looks like you're almost on the right track. And then there is some difficulties. And I didn't quite say how you get over them. Maybe a good answer is because I don't quite know. But somehow, technically, we got over them. OK, so that's that. Now I want to move on here. So the second thing I want to talk about is what happens when alpha is epsilon. So here, even defining, okay, so A is the same thing, but now alpha is epsilon, so close to 0. Close to 0. So here, even the first step of defining F by majority, it doesn't make sense anymore. Okay, so what does it mean, alpha close to 0? It means that, okay, do I have it here somewhere? I have, again, this labeling, but now I know that the probability that two subsets agree is just epsilon. So think of, some 0.01, some small constant fraction. Okay, now let's ask ourselves, do we even expect, if we have a labeling that has this kind of small pairwise consistency, is this even meaningful? I mean, how consistent is like a total random function that has no structure whatsoever? Okay, so let's figure this out. So now let's think of T as some, not not equal to 1, but equal to some slowly growing function of k. So now think of t, which is the intersection size is, I don't know, either square root k or k over 2, some function that grows with k. Okay, and now I think of f as a random function. So, f of s is some random string in 0, 1 to the k. Okay, so what's the probability that f of s on the set of intersection agrees with, this is a question mark, agrees with f of s prime on this intersection? I mean, they're looking at some t elements here, right? And the value is determined at random, so the probability of this is 2 to the minus t. Okay? I chose f completely at random. This is the pairwise consistency that I expect. So now what if you tell me, look, I'm giving you an f that has slightly better pairwise consistency, right? So this is like the very extreme end of something that's slightly non-random. Okay, so what can I deduce? So if alpha is bigger than 2 to the minus t, what can we say about f? Right? Is there some underlying global function, little f, and so on? Okay, so with Lazar, a while back, we proved that if alpha is some some polynomial in k, so I looked this up, it's k to the minus 19 over 75. So I mean, think of it as like 1 over some constant power of k. If you say, I have no idea where this number came from, but it's like in page 1 of the paper. Okay, so if alpha is some, this is going to 0, and t is also, I didn't look this up, so t is also some power of k, okay? So the intersection size is some square root of k, but it's not square root, it's k to some constant. And the success probability is some power of k. Then you have lifting. Then have lifting. Okay, so then, local consistency implies a global consistency.
But you didn't tell us what beta and delta.
Yeah, so in that paper we didn't, I don't even know if we figured it out. Like, we were happy with any kind of non-trivial thing.
But
Yeah.
some things are impossible, right? Because of the example you gave.
Right. So, I mean, what I'm not sure of is did we prove something that's just over what's impossible, or is there some gap in the parameters? I don't remember. Okay, but yeah, some things are impossible, and then we proved that the agreement is up to some polynomially small fraction of the coordinates. But I don't know if the coefficients match, the exponents match. Anyway, we had some global lifting, but also an interesting thing is that we also had a counterexample showing that if you want alpha to be more like 2 to the minus t, okay, so I guess here the correct thing to say is that alpha is a polynomial in t, because t itself is like 1 over k to the c, and alpha is 1 over k to some other c, so it's polynomial in t. So it's like you check the two local views on t coordinates, a random function will succeed with probability 2 to the minus t, but somehow you're only proving some kind of global consistency when the success is 1 over square root t. So you're requiring much more pairwise consistency before we were able to prove something. So what happens in this regime? We want to really prove that even if your success is a little bit bigger than this, already something happens. But we showed the counterexample, and I already showed this counterexample in the previous lecture. In this counterexample, you show how to split all the k-element subsets according to what is the first element in this subset. So let me just say it without writing. For each k-element subset, order it lexicographically and look at the smallest element, and then assign, let I'm now defining a capital F that kind of is a counterexample to my idealized theorem. It's a counterexample to lifting above 2 to the minus t. So capital F will be little f restricted to s for different little s. So which little f we will take depending on the first according to lexicographic order in S. Okay, so if the first element in S is 7, we define f of s based on f7. If it's 18, we take f18. And f1, f2 up to f18 are going to be random functions that have nothing to do with each other. And you can see that still the success probability here is it's actually polynomial in T, and of course it has nothing to do with some global function.
Roughly T over K.
It's roughly T over K, yeah,
So
it's true. Because you need to catch, right, so you need to catch in your intersection the element, the minimal element in your K element subset. Okay, so I mean, I went over this a bit fast, so I'm not sure. Yeah, but the point is that it's kind of a very natural counterexample, and it shows that you can only expect lifting from when alpha is some polynomial in T. So let me write it here. Alpha is a polynomial in 1 over T. We have lifting. And also cannot have lifting above some other, for alpha smaller than some other polynomial in T, 1 over T to some C. Okay, so we thought that we kind of understood what's going on. But then, like 1 year later, there was a work by Impagliazzo, Cabanets, and Wigderson, and they showed, so where will I do this? They showed that it's true that you can't have this global structure, but you can have a local structure. I mean, in this counterexample, we split the universe into many parts, but in each part, we were perfectly consistent with this F1 on in a big area and F2 on some other area. So they proved some local structure, but more than that, what they proved, IKW, they proved that if you look at the, consider the 3 uniform hypergraph, so it's a 3 query test. Consider a 3 uniform hypergraph defined as follows. What they called z-tests. Okay, so what is this? So remember, we had this, this is n choose k. These are all my vertices, and previously I put an edge between S and S prime if they intersected on T elements. Now I'm going to put a triangle on a 3 tuple of S, S prime, and S double prime if they satisfy the Z condition. The Z condition is this. This is S, this is S prime, and this is S double prime. Okay, so S and S prime intersect here, and S prime and S double prime intersect here. Okay, so for every 3, and what is the size of this? So let's think it's k over 10. Okay, so for them, it was something like square root k. Square root k is a magic number here because, I mean, maybe you can guess. If you start with S prime, a random subset, and then you select at random a subset of k, a square root k elements, and independently another subset of square root k elements, then they will be disjoint with high probability. I mean, if you have the constants correctly. Okay? And this kind of independence is very useful in the analysis. Once the intersection size is bigger than square root k, this doesn't hold anymore. And so that's why square root k is kind of a magic number. But, I mean, you can consider the z-test with any intersection size up to, I guess, I don't know, k over 3 or something. Even k over 2. It's not good to consider a z-test like this where all three subsets have an intersection, because then the counterexample will hold again. So I don't want to get into it, but it's very important that these kind of are disjoint. So they considered this z-test, and they proved lifting for z-test. They proved that if the probability over choosing this S prime, S double prime from this hypergraph, that, you know, f of S prime, f of S prime, double prime agree on intersections, so you understand what I mean, right? I mean, these two should agree on this intersection, and these two should agree on that intersection. If this probability is bigger than 2 to the minus t, so this is like what we expected. So, okay, so they don't have 2. They have here, I don't know, 0.999, some constant to the minus t. Yes, to the t, right? Then there exists some, so let's call this epsilon. Okay, we called it alpha. Then there exists a function, a global function, f, such that the probability that we really agree with f, and here again I'm neglecting the delta, this probability is also some poly in alpha, independent of, it's alpha to some constant power. You know, this is fantastic, right? So you have some local consistency with some probability that's almost like the random thing, and it's explained by the existence of some global function.
What happens if S prime and S intersect?
Yeah, that's the picture I tried to describe here.
No. Like a triangle.
Ah, like this. I don't know. Yes, you're right. So it seems to be a more powerful test on one hand. On the other hand, there's less, well, there's some freedom here still. Maybe it's better. It's a good open question. I don't know. So I will get to some open questions soon. Okay. So the triangle suggestion is very intriguing.
Yeah, but it's not clearly more powerful or less powerful.
Yes. Well, okay, let me tell you what we don't know here.
Why?
You think it's more beautiful, or? Okay, so just to say, so what did we deduce here? That sorry, we have lifting with the intersection exponentially t, but as I mentioned, the analysis t was limited to be up to square root k. So so when alpha is exponential in minus t, we have a local, how will I call it? Local lifting. Local lifting. Okay, let me just say z-test lifting for t up to square root k. So it means that we have exponential with t, but only up to square root k. Okay, and then, you know, it's an open question. What about t being, something like k, alpha being exponential in minus k, in minus t? It's the same thing. Okay, let me say t, and z-test lifting. So this is, I think, a very interesting open question. So in this work with David that I mentioned just before, we managed to make some progress on this, but not enough. So we showed in this IKW work, as I said, they showed that the IKW showed that the two the consistency graph lifting, the v-test lifting, meaning you just take S and S prime. So this is the kind of lifting that I talked about all along before we move to the z-test, implies some kind of piecewise global structure. So meaning, like the counterexample showed that there is no global structure, but piecewise there was something going on, they showed that in some sense the counterexample is the worst thing you can do, and inside each piece it's still a direct product. So in this work with David, we showed that the same thing for alpha, which is exponential in, for all the range of alpha. Okay, so basically we analyzed the v-test now for all range of alpha and showed that, for very small alpha you still get the piecewise global structure, and for very big alpha, I already told you before. So this we kind of almost understand. However, we're not able to analyze the z-test yet. Okay. Okay, so this is all that I discussed so far is about the set capital A being n choose k. Okay, so it's all, you're given the local views on all possible subsets, and then you have some pairwise consistency or three-wise consistency. You want to deduce global consistency.
Is it ever happening that this global F is not majority, or that remains always?
Oh, thank you. I forgot to say it. No, so, right. In the regime where alpha is close to 0, so even 0.1, majority is no longer meaningful, right? Because you can think of the following construction. Take two different little f's. Say even little f is the all 0 function and the other one is the all 1 function. And for every s separately, at random choose from this guy or from that guy. So for half of your s's you're going to assign the all 0 string. For half you're going to assign the all 1 string. Now what will be the local consistency? Well, probability half you will succeed. Right? So alpha here is 1/2. And the majority function has nothing to do with anything, right? The majority function would be some random function. And so, how are you? But on the other hand, this function has very good structure, right? On half of the domain, it agrees with one global thing, and on half of the domain, it agrees with something. So it's like more like a list decoding, right? You need to define several different global functions, and you prove that your function agrees with one guy in the list. So you need to first, you still want to do this kind of majority idea, but you need to first kind of condition. So the way these things are done, remember when I tried to prove this theorem for the high acceptance regime where the pairwise consistency was 99%, I said, number one, define the little f, just do majority, and now all we need to do is prove. Here, even the step one of defining little f is no longer obvious. So what you do is you first select at random some set of, k prime elements, and you take a random subset, and you see what it says on this k prime elements. And then you say, okay, let's look at all other k element subsets that contain these elements and agree with this guy. So you kind of have some conditioning. And then from these, I'm going to define the majority. Does this make sense? So anyway, you do some kind of conditional majority, and this is how you get the list. So, yeah. All right. So this is kind of what I wanted to say about the parameters for full for the set A, which is all the k tuples. But a very interesting question is what happens if you look at other families of subsets. So you try to ask yourself, you know, I want to understand this situation of lifting local views to a global view, but I don't have at my disposal the function on all possible local views. Maybe I only have some partial family. Okay? So in particular, actually, in particular, we care about de-randomized question, which means we are interested in a situation where, actually, yeah. So let me say this right here. Other families A. So now it's going to be like subset of n choose k, but not all of n choose k. And the reason kind of I became interested in this question, most of all, was because I wanted to have the same kind of lifting theorems that we have for n choose k, but for a much smaller collection of subsets. This kind of would be useful for constructions of PCPs and locally testable codes. In particular, I would like a family A that has the same kind of behavior as this for the very small alpha regime, where even small pairwise consistency already implies something. But I want A to have size that is not n to the k, but rather, you know, n to the O of 1. So not exponential in k. Okay, so this is a very, this question kind of comes from a very famous question about the sliding scale conjecture relating to some PCPs with small probability of error. But I will get back to it at the end. So let me first tell you a little bit what we know about this. So in general, I can ask, you know, for which families A, you know, characterize this, can I expect to have some lifting theorem? Okay, and you can even think of this in the regime of alpha close to 1. So this is like the easier regime. For which families of subsets A can I expect that when I have pairwise local consistency, I can always lift it to a global consistency? I mean, if the family of A is too sparse, then I cannot expect it. Okay, so so which A's have lifting theorem? And it's not really just which A's, it's also which graphs this is just the set of the vertices, right, on which I make my test, but then I need to tell you also which pairs of subsets I test. However, in this generic setting, I will always test subsets that have some non-trivial intersection. So it's really more about which subfamilies of k-sets have lifting theorems. So first collection is affine spaces. So here you do this. You identify a set of n elements with some vector space. Okay, and then you look at all affine spaces of dimension, say 2, it can be bigger. Okay, so this is your set A. Okay, so now each element in A, so each S in A, is some kind of plane, affine plane in this vector space. And so how many points does it have? It has exactly f squared points. Okay, so this is what I'm going to call K. Okay, and well, how does it make sense to think of two planes that intersect? So I guess they should intersect in a, I don't know how to draw this, sorry. Okay, they should intersect in a line, however this happens. Okay, so S and S prime, if intersect on a line. So it means that T equals F. Okay, so now what does a lifting, and we have a lifting theorem. This was also proven by IKW. So we have lifting here, even for pairwise consistency, which is polynomial in T. So what is a lifting theorem? Now it says this. Look, I have for every plane in this, so I have a vector space, and for every affine plane in this vector space, I have a local view. I have a function on this plane. So it just gives me values for all the elements in this plane. And I know that if I take two random planes that intersect on a line, they will agree on their common elements with probability alpha. Okay? So this is all I'm given. I have this labeling of each plane, and this labeling is pairwise consistent to within this probability. You can think of this as 0.9. You can think of this as 0.1. Okay? And from this assumption, I can deduce the existence of some global function on this vector space that agrees with these planes. Okay, so this is what they proved. So for this structure of planes that intersect, we have a lifting. Now, actually, this might remind you of something.
The function remains into 0, 1.
Yes. As I stated it, it remains into 0, 1. But this is also where I'm headed. It might remind you of something called low-degree tests.
What about a randomized choosing
Just the k elements at random. Okay, that's a great question. So the question is random A, meaning, you have your collection of n choose k, and you can just throw subsets into your collection A at random. So, how many are you going to take? So, when you start taking k element subsets, suppose you took some, some O of n of them. Okay, just a linear number so far. Then when you add another one, it will intersect every other subset on at most 1 point. You don't even expect it to intersect on 2 points. Right? So, how many elements in... Oh, wait.
It's like picking an induced subgraph of the original element, right?
It's like picking an induced subgraph, right. So now I want to understand, is this induced subgraph the empty graph? Right? So if the graph had an edge whenever two subsets intersected on T elements, then here, after I chose, say, n points or a million n points, the graph will still be empty. There will not be even a single edge, because for a single edge, I need two subsets to intersect on T elements. And this will not happen at random until I choose something like n to the T things. Maybe n to the T over 2, I'm not sure. So need very high density. Okay, so very is all a matter of perspective. So from my perspective, that I want these families to be significantly smaller than n to the k, then this is true. Need very high density for a non-trivial test.
What if T was like constant K?
Yeah, so it's a good question. I haven't analyzed it, and the only reason I haven't analyzed it, it's a very interesting question. It's just that, kind of my focus has always been to try to find families that have size polynomial in n, independent of k, while the size of the subset is k and the intersection is some omega of k. Okay, so this is, the only reason I only thought about these things is because those are the things that are kind of applicable for PCPs, and a random subset is no good.
Just extending what
Yeah.
T was constant.
Yeah.
And it's like you contract many vertices which are connected to one vertex. That sort of reduces T. You still have a connected.
I'm not sure I
You
understand.
pick vertices and then you sort of contract, okay, all the neighbors of neighbors are now neighbors.
Okay, maybe we should, not sure, vertices in which graph you're contracting. I guess you're contracting vertices in N. Yeah, okay. All right, so just I don't know about random subsets, but I don't know, but I do know that kind of they're not good enough for my parameters. You see that here, for example, something interesting is going on because the number of affine spaces of dimension 2 is just n squared, or so, no, I guess it's n cubed. You just need to select 3 points in the vector space to define an affine space, and so it's not the size of this family is polynomial in n independent of k. Okay, think of the field as something much larger. Okay, this is a 2. I don't know if this is clear. So, okay, this family, where does it sit? It's a subset of n choose k for n equaling f to the m in k equaling f squared. Okay, so this has size f to the m times f squared, roughly. Choose f squared more correctly. Okay, whereas our family has size f to the m, say, cubed, much smaller than this, and yet it has a lifting theorem. So it's kind of it's much more interesting than a random family in this sense. It's very sparse, but yet it has many edges in it. In a random family, you will never have any meaningful intersections, but planes do intersect. Okay, so. Okay, so this should remind us of, or some of us, of low degree tests, which predate this kind of lifting theorems. In a low degree test, we also look at, say, affine spaces of dimension 2. So we have, A is still the same thing, affine dim 2. But now we have a function which is, it assigns each space not like a 0, 1 to the k kind of thing. Instead, it assigns it some low degree function on S. Okay, so f of s is assigned a low degree function on the corresponding affine space. Okay, so on 2 variables in some sense. Okay, so what is going on here? So first of all, the low degree function is over some field, so it's no longer 0, 1. Okay, so the fact that I all along talked about 0, 1 bits, there was no reason for it. We could have been talking about some other alphabet all along. Okay, because you have some n elements and you have opinions about them. The opinions don't need to be binary. They can be over some other alphabet. So this, let's assume it's the same as before. So the main difference, though, is that I'm only allowing low degree functions. So it's like before, in all the settings throughout today's lecture, we were doing, this kind of some function on S, right? Because I said like 0, 1 to the S was a function from S to 0, 1. And if I change the alphabet and it's some, I don't know, like a field, it's just a function from S to, some arbitrary function from S to the field. But now, I'm restricting a little bit more. And I'm saying, look, your local views, yeah, you can have different local views and you only have some partial consistency. But there's also some restriction on your local view. You can't be totally crazy. Your local view must have some kind of property itself. Okay? For example, it must be a low degree function. Okay, so you're imposing a little bit more structure on the local views. They're not some arbitrary string. They have to be of low degree. And you can, of course, generalize it and, think of here as having some domain, some domain K that has some interesting structure, and then ask if you have lifting. In general, this should make your life easier to prove lifting, because if the local views are restricted, then maybe you have a restricted local view and pairwise consistency, then maybe, more lifting can come. Okay? So indeed, in low degree tests, this is exactly the kind of theorems people proved. Rubinfeld-Sudan, and then further ones for small alpha, Aurora-Sudan, and Raz-Safwa, proved that if you have such a function, and if on two random planes the functions agree with some probability, there is some global low-degree function that agrees with everything. So here, you also expect the conclusion to be stronger in the sense that the global function has also structure. It's low degree. This is why they're called low-degree tests. You have pairwise consistency, but on low-degree things, and you deduce global consistency on a low-degree thing. So here is some other example that I don't know, but I expect that these things to maybe hold. So let's think of this situation. So I'm moving now back to the situation of to some k, which is a subset 0 into the k. Okay, and now I want to suggest a specific family A. So the way I want to do it is I want to imagine I have some big graph on L vertices. So there's, L choose 2 possible edges. So I'm going to call that N. Okay. And now my local views are going to be local views of the graph. So I'm going to look at graphs on K, I guess, how should I call it? L prime vertices with K equals L prime choose 2 possible edges. Okay, so the picture I have in mind is there is some graph G that I don't know. Okay, and maybe there is an edge here, maybe there isn't. So I don't know the value of whether or not there is an edge is my function little f. So little f is describing this graph. Okay, so f is a function from n to 0, 1, indicates edges in the graph. Okay, and then my local views are going to be choose some set of L prime vertices, and then there's how many potential edges are there? There's L prime choose 2. So f is a function from n choose k. Well, it's not all of n choose k. It's this. I'm not choosing all potential k tuples of n. Only k tuples that are incident on the same set of L prime vertices. It's what? It's the size of A is L choose L prime. Okay, which is it's smaller than n choose k, I guess. All right. 0, 1 to the k though, right? Because you choose L prime vertices, but then you need to specify your opinion on all the edges, which is k possible edges. And now I want to say, okay, can you lift this? So if there's pairwise consistency here, can you lift it to a global consistency on F? This is just some specific example. But here in this example, you can see that, you can ask all these property testing type of questions where you say, but I'm only allowing local views that are triangle free. And now I want to know whether I can lift this to a global function that's triangle free. And so on and so forth. So I'm just suggesting this in this talk. It's not like I don't know anything about this. But there should be reasonable theorems like this. But yeah, I don't know. Okay, so I guess I'm all done. Okay, let me collect another couple of minutes. Okay, good. So, all right. So, as I said before, but now I want to finish with this, is like stating it as an open question. For a long time, I was interested in finding these kinds of subfamilies A, for which you can prove a lifting theorem when the alpha is very small, exponential in K. So kind of my goal was to find a subfamily of K subsets such that if you have pairwise consistency on them, it implies some kind of global structure, even when the pairwise consistency is exponential in K. We already know this for the set A being all possible K tuples. So it's the kind of things that we have here. So we know this, even if I imagine that I knew this for all values of t, it will still not be what I want because the collection of K tuples has size n to the K. And kind of the use that is very useful for PCPs would be that K is super constant and you want the size of the instance to still be polynomial. So now, after failing for a long time, I want to make the following conjecture that actually there can be no such lifting. Okay, so this is what I want to end with. Okay, so in general, it is interesting to understand when does lifting hold? When does lifting hold? Can you characterize or even find a subfamily of A's for which you can prove that lifting holds under some general conditions? I think this is a very interesting question. And the more concrete question is to show that if certain parameters lifting does not hold. So this is what I want to state now. So in particular, I conjecture that if A, okay, so we have a family of K element subsets, and the size of A is just some, I don't know, n to the 10 at most. Okay, so some constant that is independent of K. Then for T, which is some theta of K, okay, maybe I should be more explicit. Okay, there can be no lifting with okay, let me write it like this. For T, theta of K and alpha, which is exponential in T, no lifting. So what this means is that whenever you have a global function, you can have a global function that is pairwise consistent with this probability and have no global reason. So for any A, there exists some f from A to 0, 1 to the K, such that on one hand, the probability that f of s on the intersection for I choose S and S prime from A. These are in A. On one hand, this probability is bigger than alpha, but there is no function agreeing with F. And in fact, to make this conjecture stronger, I want this to even hold for all, even for any R uniform hypergraph. So I mean, I'm also allowing like z-test and triangle test and everything you want. And if so, you get more. You know that even under the triangle tests, alpha fraction of them succeed. Still, there will always be some counterexample. So yeah, I think if it is true, then it should be provable. But who knows?
For a long time, you believed that it is false.
For a long time, I tried to construct these things, and I asked my combinatorial friends to find me these potential families A, but there is no suggestion even, and yeah, kind of
Cosets in some groups.
corsets. So I need to know what that is. Cosets of a group. I say, yeah.
That's the affine.
Yeah, the affine is very bad in this regime, just because the alpha that it works with is not exponential in F. It's like polynomial in one. There's F points in the intersection, and you only have this alpha to be polynomial and not exponential. So yeah.
I have some arithmetic question.
Yeah.
In some branches of mathematics, you define manifolds only by local views, which
Okay.
is Riemannian manifolds, and you don't worry about lifting at all. You want to define quantities which you can define only
Locally.
by the local
Right.
picture and the consistency between them.
Right.
And then you can study this global.
Then you can
properties.
study global properties of these
Yes,
things.
you can. That's the main reason for the definition.
I see.
Yeah,
Yeah, I mean,
the Riemannian manifolds, for instance. You don't worry about the lifting at all.
She does.
Yeah.
It's in different direction. I mean, the global things exist because there is consistency between the local pictures.
You have perfect consistency, but here I don't have perfect
usually
consistency.
In differential structure and so on, which you can define by local views, and everything is perfect.
Yeah, so let me just end by saying, you know, Eli, that the reason I find this so natural is because a lot of times it's more convenient to define something on a local scale, because this is the scale you have control over, and then you hope that something global is also going on, right?
Yeah, but
So
you don't assume there is some global function.
I mean, okay,
Okay.
all right. Well, thank you.